since the title doesn't necessarily convey everything, and to help make sure that you're in the right room, I'm going to read through the abstract, kind of explain it a little bit, and then if that's not what you're looking for, you can take off if you want to, but that's up to you. So let's see. That's not supposed to be there. There are as many ways to design software as there are projects to design, but there are guidelines you can follow to keep things moving smoothly for your users and systems alike. One of the most straightforward things you can do is separate quick tasks from slow ones, keeping the quick ones closer to the user and moving the slower ones further away. There are several tools to simplify this process depending on which language and environment you're working with, but this talk will focus on the architectural concerns involved in designing and building software this way, especially in online environments. So what that means, because word vomit doesn't necessarily mean anything. I had a lot more expansion on this that my brain has now dumped. So a lot of projects that I've encountered using the web, using desktop applications, I find myself sitting on a loading screen or otherwise waiting for the application to do something, and I don't necessarily have any feedback that anything's happening. And being a software architect myself, it kind of annoys me that they haven't taken that into account and designed with that kind of fail condition in mind. Simply by taking these long-running tasks and moving them into a background process and allowing me to continue doing other things while I wait for that to finish, my user experience would be vastly improved. So I'm going to look at a few ways that that can be designed into your application before the programmers even get to it. So the main problem is that the more functionality you add, the slower your application goes, because you've got tasks that take a while and you've got to wait for them to finish before you can move on to the next one, or you're trying to do 100 different things at once and your application is trying to get all of them completed before moving on to the next one. Now, slow applications don't scale. That kind of goes without saying. It's something that's probably going to be printed in fortune cookies before too much longer. So, but it is a good reminder that if we allow our applications to get slower and slower and slower, our ability to use them at large scales is going to decrease more and more and more. So we don't want that. So in order to solve this problem, we need to break up the functionality. We take the stuff that runs nice and quick, and we keep it up near the user where they tell it to go, it goes, it comes right back to them, and the user continues on with what they're doing. And the slower stuff, we move into the background. Run subtasks in parallel. A lot of applications are doing things one thing at a time in order, and there are a lot of technologies that exist for allowing us to do more than one thing at a time. And the more of those we use, the faster our applications can go because there's extra processing power not being used otherwise. And we can even amplify that more by distributing processing across multiple systems, especially in an online environment. So breaking it up, ask yourself some questions about the individual portions of your application. Which parts require real-time execution? Which parts have to be done in a certain order? Which of these parts have to be done the way that we've been doing programming for decades? Those go in one pile. Which tasks can be deferred? Which ones do I not have to do right now? Sending emails are a task that can be deferred, that usually that's not what's going on. So that one's my pet example for deferred tasks. Which tasks can I run asynchronously? Now, these aren't always things that you've deferred, but let's update the data on the current page from the server. That can be done asynchronously. You don't have to wait for the result before you can move on to whatever it is you're doing next. And then what tasks can I delegate to other systems to take advantage of the fact that I have a server? Which tasks can I have the server do so that the browser isn't doing those? Or if you've got more than one server with which distributed processing would imply, which tasks can I make other servers do so that as the main backend server that the front end is communicating with directly, I don't have to handle those. And those will be separate piles of tasks that your application is going to need to perform. And then you're going to take each of those tasks and you're going to drop them into a black box. Now, a black box, the term comes from a device on most aircraft and many water vessels that records a whole slew of data about what that particular craft is doing. The idea being that if the aircraft goes down, you can pop open the black box and look through the information that was recorded to see what happened as the aircraft crashed, or whatever it was that happened to whatever kind of craft you're looking at. So you can reconstruct the problem and actually figure out what went wrong so that you can then prevent that problem from happening again in the future. Most of that is actually dropped out when we talk about a black box with system architecture and with programming. Basically, we just keep the portion of the definition which is we have no idea what's inside. We have no idea how it does what it does. All we know is we give it these inputs and we get these outputs back. So a black box in the realm of programming is just a discrete unit of code that does something and you don't have to care how. So anything that's asynchronous or deferred or otherwise, we can take this and move it out of the main logic flow of our application, goes into its own black box, each individual task. That way, none of the other parts of the system have to care how those particular tasks are going to operate. And then, of course, your main application is its own black box. None of your tasks should care how the application functions as a whole. They should simply be told, hey, give me this information based on these inputs, and give the result back. That allows you to maintain each of those black boxes independently of each of the others. Then those boxes do need to be able to communicate with each other. So you have commands that you can send to each of those individual tasks. This is what I want you to do. Here's the information I want you to process. And then those black boxes need to be able to report back a status. So I'm waiting to perform my work. I've started or am starting in some systems. I have finished. Something went wrong and I failed, or something interrupted me before I could finish. Are the most common. There are other statuses that you may find useful, but those, again, are the most common. And then, of course, your data that you return back from the black box to whichever part of the application requested it. Like I said earlier, there are multiple tools for parallelizing your tasks. We've had threading and forking on various systems for several years. Threading is fairly recent on most Unix systems, forking having been the preferred method for a long time. Forking has some limitations. You have to copy the entire process, but it is a complete duplicate of the entire process and picks up with the exact spot that you forked from. So there's some advantages there. But threading is a little bit less resource intensive. It allows you to create a separate application space which isn't a full replica of the whole process. Threading on Unix systems is still a little weak in some areas, but it is mature enough now that it is a viable option. When you go to Windows and certain other systems, forking is not available, so threading is the only option you have. One of the other things you can do with parallelization is remote processing. RPC is a common acronym that goes along with that. It won't be used very much longer, but I threw it in there anyway because this is, well, anyway, I haven't removed it basically. But with remote processing, you can say, hey, I want this task done, and talk to a completely different system when you do it. It allows two completely disconnected systems to talk to each other. A relatively new approach to this is known as the queue and worker approach. You queue up a list of tasks, and then you have one or more workers that work their way down the task list, performing each task one at a time. Generally, you're going to have several workers in a pool working on the same queue so that you can process each of those jobs more quickly by doing them simultaneously. Now, the webs and workers approach is a way to basically bring all of this together into one place. You use the queues to schedule your tasks, and then you use workers to monitor the queues and actually perform the tasks. You'll have forking or threading inside of your workers in order to isolate the tasks from each other so that they don't step on each other, or so that if one of them breaks catastrophically and crashes, it doesn't necessarily kill the worker. But even if it did, then the other workers are unaffected. And then running workers on multiple systems allows you to do, again, to distribute that load much the same way that remote processing would allow, so that you have even more isolation, but you also have more ability to parallelize and run things simultaneously because they're not competing for resources on the same system. We have several API protocols depending on what kind of application you're building. Inter-process communication is used in desktop environments or within a single server for the different components to communicate with each other. There are myriad forms of IPC, the simplest of which are just simple signals saying, hey, stop executing, or pause execution, things like that. More commonly in the web environments, you'll use HTTP and send a payload in HTML, XML, JSON, what have you, between the browser and the server. The browser will send a JSON payload up to the server. The server will perform whatever task is indicated by that particular endpoint, and then return a response in whatever format the browser is expecting. Let's see. The shared queue itself is the protocol for communication between the webs and the workers. The web interface, or the back end anyway, will actually queue the tasks. It'll add tasks to that queue. And then the workers will communicate with the web by pulling tasks off the queue and then posting the results back to a different, usually shared location with where the queue backend. So for example, there is a queuing engine called Rescue, which is written in Ruby. It was a project created by GitHub. It has several ports to other languages, and it uses Redis as the storage backend. And so generally, a project using Rescue will store the status information in Redis as well. And then all of the different worker systems, as well as your web backend system, will have access to that Redis server and communicate that way. Most other applications, especially embedded ones, are going to have something custom built that is probably closer to IPC. But if they're communicating over the web, they'll probably fall back to the HTTP. Although there are other protocols available for specialized use cases. So really quickly, I'm going to run through an example just to kind of show how to break apart an application using these principles. So the example is a user-triggered report generation. You've got your application, you've got a bunch of data, and the user wants to generate a report. So they go into their user interface, they go to the reports page, and they say, hey, I want to see this report. They click the button. In some systems, what would happen next is the user would sit there on a please wait with a GIF of a spinner, and they would wait and wait and wait until the report is done. But a better way is to, when the user clicks the generate button, the website says, okay, I'm generating this. Go ahead and continue doing other things while I work on this, and I'll let you know when it's done. From that point forward, the user can navigate around to the rest of your application. And your application is polling the server saying, hey, is this job done yet? What step is it on? Depending on the degree of granularity you have for that particular task. And the server responds back, okay, I've queued the job, but it hasn't been pulled off yet. It's still waiting. It's in a wait status. So your server gets the request to generate that report and throws it on the queue, obviously. And then the queuing engine, or excuse me, your workers, not the queuing engine, your workers are monitoring the queue, so as soon as they see that task and get to it after processing other tasks that were queued before it, will actually pull the task off the queue and say, hey, I've started this. And it will actually generate the report. And then when the worker is done, it will pop the status back onto whatever stack it needs to be put onto. And the server will check that and say, oh, it's finished. Here's the report. Your front end is continually polling, hey, is this done yet? Hey, is this done yet? Hey, is this done yet? And when the server says, hey, yes, this is done, your application then says, oh, hey, by the way, this report that you asked for is finished. Go ahead and click here to take a look at it. And then they can click on the link that's now visible and go to that report. And that's just one example of how that would work in practice. So are there any questions, comments, or other feedback?
So why wouldn't you have the server push those updates? Oh, it's being queued. Oh, some worker got the task. It's now working on it. Now it's pushed.
You can absolutely set it up to use push. That's still a technology which is not adopted as thoroughly as it should be. So a lot of applications are still using polling instead. But absolutely, you could use pushing instead. There's nothing stopping you from doing that.
Do you have any, I know you mentioned the one technology from Ruby that uses Redis.
Mm-hmm.
Do you have any comparisons for any other technologies similar to Redis that would be able to handle like the message queues?
There are a large number of key value and similar database technologies that would work fairly well. I try to avoid relational database systems for that, mostly because one of the main advantages of using Redis for something like that is you have atomicity. You can guarantee that when something's been pulled off the queue, it's no longer on the queue. You don't have race conditions for, okay, well, I found this. Now I've got to issue a separate command to remove it. And in that small span of time between seeing that there is something and then removing it from the database, another request could come in from another worker and pull the same job. So I don't recommend relational databases for that because they usually can't guarantee atomicity of the data. Whereas I know for certain that Redis can, and most other NoSQL database systems that are probably some SQL database systems as well, some newer ones, which have been designed with that in mind. But most of the NoSQL ones actually do support atomicity out of the box because of that kind of a problem.
And how are they able to handle like failovers? So if you have a node that goes down, is it able to transfer the messages over to somewhere else and then still be able to handle giving a response back to the clients?
That'll depend on which storage engine you're using. Redis actually persists to disk, and it doesn't do it continuously, but it does it periodically, and it's configurable. So it can be anywhere from every second up to every 5 minutes.
But if you shut it down, then it will persist it?
If you shut it down normally, it will persist everything to disk, and then when it comes back up, it'll load that back from the disk. If the power,
it will just continue on through the queue.
And it would just continue on through the queue, yes. If the power goes out, you lose however long it's been since the last persist operation. So
what are your thoughts on, I mean, there's lots of systems that can act as some sort of a broker, right, for message exchange. What are your thoughts on using something that's more active, say like a RabbitMQ style broker rather than a Redis, a simple key value store?
I don't have a lot of experience with most of them. Rabbit in particular, I don't have any experience with yet. However, it's from what I do understand, those systems are designed to do more of the work. So a system like Rescue is doing a lot of the, okay, I need to add this to the queue, and then I need to pull it off of the queue, and I need to check the queue to see if there's anything on it in the first place, and all that fun stuff. Whereas the brokers that are designed with that in mind handle all of that internally. So it's just, it shifts the burden of responsibility from one library to another. So those are some really nice looking technologies though.
Yeah, The reason I ask is we just implemented a fairly large distributed system making use of RabbitMQ, and it's really nice. There's a lot of things you can do, and the component of it that I particularly like is rather than having workers polling the system, we can actually do push.
Yes, absolutely.
And so you can chain tasks together into long, complicated arrays, manage the branching. I like it. I'm curious. We have not, in relation to your experience, I haven't had experience using simple key value pairs. I'm wondering.
Yeah. Redis can simulate some of that. It has a publish subscribe feature that would allow for pushing. And it also supports blocking pops. So it'll sit and wait for something to show up and then return control to the program. But those other solutions are definitely designed for as soon as let me notify somebody. Yeah.
When you're dealing with this kind of an architecture where you have like your queue, right, your Redis or whatever, and then your workers that are handling those requests, how do you deal with the architecture of like your clients adding stuff to the queue or requesting data or whatever it is? Like, do you have them access the Redis directly, or would you do it like through an API that then goes to Redis that then breaks it out to the workers that are connected to Redis themselves, or how do you design all that?
It really depends on what it is that you're trying to do. In the example that I gave here, your user interface, actually your browser app, tells the server, hey, I need this report generated. And then the server, so it's basically an API call. And the server puts the job on the queue and then monitors the status until it comes back.
And then your workers, they're connected to that queue?
Yes, the workers talk to the queue.
I handle these messages.
Yep. But if you're doing something different where it would make sense for the user to actually be able to see the queue, then you would connect them a little more directly to that queue. So.
I'm not sure if your architecture handles this, but I mean, when you get to a certain level of load, how do you scale this out? What are strategies for doing that?
Well, there are numerous strategies. Some of them are outside the scope of the presentation, such as adding more back-end servers, and getting those to coordinate is not always an easy task. But you can add more workers to the pool, and that will allow you to scale horizontally that way. Generally, that's about it as far as within the scope of this particular presentation. But normal scaling practices would still apply.
It seems to like setting your application up this way, where you do have kind of this abstraction disconnect between the front end and all the heavy lifting work, would allow you to, if you needed to, go in and add more backend servers. You've already got a kind of an application framework that's set up to bounce things off that direction.
Yeah,
at least generally speaking.
Yes, absolutely. That's one of the main benefits, is that you can manage your resources on your end a little bit more easily and with more transparency to the end user.
Sure.
Just as an example, picking out, you give an example of sending out an email, not necessarily has to be a synchronous one. We have done something in our application where exactly that, we don't want to utilize our user-based servers, user activity-based servers to send out emails or do any processing of sending out emails. Not just email, even the content and everything that has to, there's a lot of processing that needs to be done, like the tag processing and so on.
Yes.
So we move that off to RabbitMQ, worker threads will take care of sending out the emails, making the content of it, and then send out. So that's where it gives a nice feature of consistency, or the data is available. Even if something goes down, you can come back up and send it out again. And also, it takes out the burden of all this resource consumption by just the amount of sending the emails, and it's more resources for the users to use.
Absolutely. Yep. If nobody has anything else, this is how you can get a hold of me if you'd like. And that's all I had.
Okay.